Hello everyone, and welcome to Soil Moisture, Why Water Content Can't Tell You Everything You Need to Know. Today's presentation will be 30 minutes, followed by 10 minutes of Q&A with our presenter, Colin Campbell, whom I'll introduce in just a moment. But before we start, a couple of housekeeping items. First, we want this to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, don't worry, we're recording the webinar and we'll send around a link to the recording via email within the next 3 to 5 business days. All right, let's get started. Today we'll hear from Dr. Colin Campbell, who will discuss how and why scientists combine both water content and water potential sensors for more accurate insights. Colin Campbell has been a research scientist at Meter for 19 years, following his PhD at Texas A&M University in soil physics. He is currently serving as Vice President of Meter Environment. He is also adjunct faculty with the Department of Crop and Soil Sciences at Washington State University, where he co-teaches environmental biophysics, a class he took over from his father, Galen, nearly 20 years ago. Colin's early research focused on field-scale measurements of CO2 and water vapor flux, but has shifted toward moisture and heat flow instrumentation for the soil-plant atmosphere continuum. So, without further ado, I'll hand it over to Colin to get us started.
Thanks, Brad. It's great to be with you here today to talk about why water content can't tell you everything you need to know. And I'm also really excited because we've got almost 1,100 people signed up to listen to this. And I think it's really important, and I'm excited to talk about it. As a 12-year-old boy, I joined many of my friends on a winter hike into a snowbound cabin near the top of a beautiful mountain. After a fantastic afternoon of sledding, our soaking wet group of boys trudged back to an icy cabin and hurried to build a fire to try to get warm and dry out. With the fire built, we continued to add logs so that we could be comfortable, but way overshot the mark. Soon the cabin was sweltering, and instead of relaxing by the glowing fire, we were overheated and sweating. The fire was so hot that some of the boys' boots melted as they dried on the hearth. In an attempt to cool down, we let the fire die and were soon shivering with the cold and struggling to stoke the fire again. Clearly, we misunderstood a fundamental thing about how many logs we needed to add to the fire to keep us comfortable in the cabin. In fact, relating the quantity of heat to our comfort level is a very difficult task indeed. Think about this. Without more information, we cannot tell how many logs will keep us adequately in our comfort range. Now you may say, well, you know how you feel, so you should be able to know how many logs to add. But I would counter that that's actually more information. Let's keep talking about this. A professor named Warren S. Johnson from Wisconsin in the United States had a similar problem in the late 1800s. Finding the janitor to add coal to a furnace downstairs to keep his students comfortable was an imprecise and time-consuming exercise. Instead of trying to calculate how much heat to add by knowing how much heat coal contains, the size of his room, and how much heat there was there already, he simply invented a thermostat. This invention used temperature and a bell down in the basement to alert the janitor to add more coal when the room dropped below the comfort level. This 1883 invention was the primary product of Johnson Controls, a company that's actually still in business today. Controlling soil water for plant growth has many parallels to these stories. Often people managing irrigation recognize that a plant is struggling in dry soil and add water to make the plant comfortable again. But they overwater, not knowing how much water to add, and move the plant from parched to drowning, repeating the cycle over and over. It seems like there'd be an easy fix to this problem. If we monitor the amount of water in the soil with a water content sensor, then we could know how much to add to keep the plants comfortably in their optimal range, right? Well, although knowing how much water is in the soil is important, It has a similar problem to the story about adding logs to the fire. How much water will be enough? The answer to that question is the same answer of Professor Johnson for the control of his room. You need to know something that, like temperature, will tell you about the energy state. Everyone is familiar with temperature. We constantly use it for checking all kinds of decisions. But in doing so, we rarely, if ever, think about its complicated definition as the energy state of a system. We simply know what it means to our comfort and how it impacts systems of interest, and are satisfied with the units we're passed without necessarily knowing how they're tied to the third law of thermodynamics. Water potential is a far less familiar term that defines the energy state of water in the soil and is analogous to temperature. It defines the water comfort level range of plants in the same way that temperature defines the comfort range for humans. Simply put, it is the thermometer for plants. Some resist using water potential because it's hard to understand. But while its definition may be a little complex, comfort ranges are well established, so there's no absolute need to deeply understand the measurement to get the benefits out of using it. So I'm showing you here a table from the book Physical Ediphology that was published in 1972 by Sterling Taylor. And many of these ranges were actually established many years before, probably before most of you were born. But if you look on this table, and we were interested in growing potatoes, we could see that potatoes thrive best, or their optimal range is about -30 to -50 kPa. Now, that range could be just a little bit squishy, so I've made a little thermometer to the range that I think maybe more represents general plants, which is -20 to -100, or general agronomic plants, I should say. In yellow, I've noticed there that the stress range. This may last, for example, from -100 to -500, or even close to -1000 kPa. You also notice some yellow up near 0. That's because plants don't love to have their roots totally soaked all the time either. So that's our goal. So why isn't water potential used more commonly? I've asked a lot of people this, and I've found these are generally the answers I get. 1, water potential is difficult to understand. 2, water potential is hard to measure. And 3, even if I use water potential, I still don't know how much water to add. Now we're going to focus on each of these challenges. One thing I want to note here before we dig in is to tell you who are not necessarily irrigators or agronomists that please be patient with this discussion. I'm going to talk about water potential in terms of agronomy, but I think there's still a lot to learn for natural ecosystems. In fact, I'm currently working on a paper together with several colleagues to publish how water potential impacts a natural environment in the Rush Valley Desert of Utah. So just stay tuned with me. One of the things that creates this fear and misunderstanding of water potential is unit overload. All these units are units of water potential and are common in the literature. Kilopascals, bars, atmospheres, millimeters of water, megapascals, joules per kilogram, centibars, and PF overload our understanding and get us to ask, what do they all mean? Well, I could sidebar on this discussion and talk about how to relate each one of these to each of the other, but I don't have time today. We'll get into that in another virtual seminar. For us, we're going to move on and just address this statement that water potential is hard to understand. Think about temperature. Temperature is defined by the third law of thermodynamics with respect to molecular movement at absolute 0, blah, blah, blah. That is a definition that most of you didn't even think about the last time you looked at temperature. You simply learned the relevant temperature unit and the scale and accepted the values for optimal ranges and moved on. There was a complicated definition, but you didn't really need to know that to use the temperature or use the temperature system. Water potential is the same way. If you watched another one of our virtual seminars, you'd find out it was the energy required per unit quantity of water to transport an infinitesimally small quantity of water from the sample to a reference pool of pure free water. And many of you probably almost fell asleep in that definition. But we can forget about that. It's true, and I know it, and I've studied it in physical chemistry. But it's not important to use water potential effectively. To use water potential effectively, we simply need to learn the relevant water potential scale that we're going to use, the units, and accept literature values for optimal ranges. Number 2, water potential is hard to measure. Well, this is actually a true statement. This is something I've worked on for most of my career. Many field sensors, for example, are inaccurate, those on the market. Some are quite expensive. There are inherent sensor-to-sensor variability in some sensors, and the most accurate sensors that we have, the tensiometer, have a very limited range. This is not even extended to the plant optimal range, up down to negative 100 kilopascals. One other problem that we should note is a poorly calibrated water potential sensor is just a water content sensor. It's going to give a relative response, but won't tell you if you're in the right range. The meter group has worked for a long time to make a sensor that can be accurate in the soil and overcome all the problems that I mentioned. This sensor that I'm using and we'll talk about throughout this presentation is called a Teros 21. These sensors are individually calibrated in a process that we've perfected over the last many years. It covers a broad range of water potential that goes well beyond the permanent wilting point. And there's an incredibly low sensor-to-sensor variability in the field. I was so excited about this particular thing, I just wanted to show you some data I've collected. Here's data from 2 different experiment sites. One of these we'll actually talk about a little later in the presentation. We're showing matrix potential here on the y-axis and time on the x-axis. Both of these were installed in the spring where no plants were growing on the surface and the soil had been re-wet after winter. You notice that all the sensors agree quite well in these 2 different studies that were in different years, in fact. And so we have great confidence of this low sensor-to-sensor variability because all the sensors are reading near field capacity and all very similarly. Now to the third point. Water potential lacks connection to how much water to apply. This is true, but we can overcome this challenge in a couple of different ways. And I'm going to talk for most of the rest of the presentation about these things. Now, just to let you know, we're going to have a quiz right at the end of this presentation. So I want you to pay careful attention to this discussion and see if you can get the question right. The scenarios we're going to consider would be what I consider a good scenario by simply using water potential to know when plants need water. And then a great scenario when we use water potential and water content together to get a complete soil moisture picture. Now I want to make clear some of the importance of what we're going to talk about. You may be thinking that water potential is a relatively important thing, but not sure how it applies. So I want to start off with why. Why does it apply? These are potatoes grown in a potato field on 6 sites. These 6 sites, we measured the water content and water potential during the entire growing season of the potatoes. After we killed off the potatoes, we harvested them. So they actually go through a vine kill to get them ready to be harvested by the potato harvester. And on that potato harvester, we had a yield monitor. So we could know the yield at the exact spot we made these measurements. And those things, the 6, 7, 9, 10, 11, 12, those are all different sites in this 35-hectare field. As you see in this graph on the left, the yield on the y-axis and the days below negative 100 kilopascals of water potential are in other words, days in the stress region is graphed on the x-axis. There's a clear correlation between the days in stress and the yield. This is really critical for us to understand because it's going to influence how we decide to use water potential. Here are data from this experiment. On the upper left, I'm showing the water content through the whole season, and bottom right, I'm showing the water potential at those same locations throughout the whole season. The graph on the left shows water content that in this particular soil, which was a clay loam, it didn't change for most of the season. In fact, as I talked to the grower who was working in this field, he wondered why they didn't change and thought everything was going well with his field. In the bottom right, we see water content changing significantly down into the stress and wilting region for 3 out of the 6 sites we're measuring. I put that little water potential, quote, thermometer, unquote, up top so you can remember what ranges we need to be in. Those systems that were actually, or those locations that were actually in the stress range, we saw also yielded much less than those in the optimal range. So we know how important this was. Now this grower, after seeing these results, the next 2 seasons has been putting water potential sensors in all of his fields to try to control irrigation. So here are data from Zenter Cloud, Meter Group's online cloud system for storing and displaying data from actually this year. The green section is the optimal range he set up, which is a little bit skinnier than the one I'm showing in the thermometer on the right-hand side. These are from potatoes grown in southern Idaho in the United States. And these are actually seed potatoes, which really rely on quality more than yield for successful incomes. What we can see is through the whole season, the grower actually held his potato irrigation in the green zone most of the time. And while we do see some of those fields exiting that optimal range, they didn't do it actually for a very long time, and he saw great yields. In fact, I talked to him from this year, and he said a few things about what he saw in the field. For his potatoes, he saw improved yields, higher quality, reduced variability, and lower diseases in each of these fields. By the way, those fields I've marked there on the map on the right-hand side. There are 9 of them, and they're several kilometers apart. For his inputs, he was able to reduce water and fertilizer application while lowering pump costs, and I think this was the most important thing to him, he walked the fields less frequently. This means he was only in the field every couple of weeks instead of what he used to do, which is every couple of days. But this did pose a challenge. This required the grower to know absolutely how much water he was putting on so that he didn't overwater these fields. He's a pretty good grower and had great familiarity with the soils he was working in. What if we don't have that? I want to talk about a great version of this effort. What if we united water content and water potential together? Now, this is a really busy graph, and because of that, I'm going to pull it apart and we're going to talk about individual sections of it in a moment. But first, I just want to tell you what you're looking at here. On the left-hand y-axis, the soil volumetric water content, going from about 0 to 40%. On the right-hand y-axis, this is matrix potential in kilopascals. And of course, we have negative signs here. As this gets lower and lower, it gets drier and drier, just as I've shown you all along. This is actually a turf grass grown in a loamy sand soil. So this is a very coarse soil, and the reactions of the water content sensors and the water potential sensors are going to really represent what we might see in such a coarse soil. We're going to talk about 3 irrigation regimes. One is a calendar-based irrigation period. Another is a fixed drying period, or kind of an optimal irrigation period. And then this is a drying period where we dry until the turf grass stops taking up water. And on this graph, we're showing 3 different measurements of water content, one at 6 centimeters, one at 15, and one at 30. And our water potential is at 6 centimeters and 15 centimeters. So we're going to jump in and talk about these specifically. Here's an over-irrigation period. What we're seeing here are periods where when we irrigate, we can see jumps in the 6 centimeter and the 15 centimeter water content. And even this is such a coarse soil that that water moves through very quickly. We even see what they call a syringing period here, where they're actually applying water during the day just to cool off the grass. So we can see that in that 6 centimeter measurement. Now down here at 25 centimeters, we see this very rounded jump in water content. That's pretty typical to see as we get lower in the soil. And that rounded water content tells us that we're getting water that's moving beyond the root zone, which only extends to about 15 centimeters. We see this also in the water potential where we're not changing the water potential really at all. This is indicative of the fact that we're overwatering, and that overwatering is causing the water potential to just be flatlined at its maximum value. Now we'll go to that middle irrigation section, which we're going to call optimal irrigation. The first irrigation event we have here on July 14th, this actually did get a little water down at that 25 centimeter level, and we didn't change much the water potential. We see that still flatlined. But here, another irrigation event, as we backed off some, we didn't get that typical jump at 25 centimeters, and we did return the water potential to an optimal range. We also get to see this water content pattern that's pretty cool. So during the night, we have flat water content, no water being taken up by the plant, and every daytime we see this loss and this beautiful stair stepping down, especially at 6 centimeters where the bulk of the turf grass roots are. We also see it at 15 centimeters, and either the turf grass is not using the water down there yet, or as we saw when we dug down, there's just not many roots at 15 centimeters. Now, one thing we can learn from this graph is when we irrigate back to the top and we are right in the optimal range of water potential, but not too much, we're not oversaturating the 25 centimeter sensor, we can call this maybe our upper limit of water content that we want in the soil. Pay attention to that 16% over here because we're going to use it later. Now here's that dry down period where we waited till the turf grass stopped taking up water. We're going to call this under irrigation. Again, we're talking about the same thing here. Here's our 3 water content measurements. Here's our 2 water potential measurements. And by the way, just as a note, it says matrix potential over here. Matrix potential is one type of water potential, and it's the only type that matters here in this soil. If you want to learn more about some of these different types of water potentials, just see another virtual seminar we've done on this specific topic. Now, something interesting about this water at 6 centimeters is we see this daily uptake, and then it stops right here. And that's interesting. Here, we stop taking up water. We are not washing water down to the 25 centimeter depth. We know here, again, we'd return that to about a 15 or 16% water content. So we're doing well on that side, on the upper level. But that stopping to take, the plant stopping to take water may mean that we reached a point where we're causing this grass to go into dormancy. We're going to note that on this water potential line here and say that the grass, when it stops taking up water around negative 500 kPa, that's its lower point that causes it to go into dormancy. Now, one thing that you've got to understand is that this flattening out of this line could also be because it rained on these several days, right? And if it was raining, then obviously it wasn't going to take up water. But of course, we've seen that the grass would jump up in water content if it was raining. Well, wait. What if it's just really cool? It's not raining, but heavily overcast. Okay, maybe there could be other reasons for this flatlining here. So we got to be a little bit careful. But the fact that we see the water potential changing and it's going into the stress range would strongly suggest we hit a point when the grass no longer was taking up water. So that's our lower point, negative 500 kPa. Some of you are familiar with this water potential, these water potential ranges, and say, hey, wait a second, it's not negative 1500, which is the permanent wilting point. Well, that's a rough guess. We can't take that as the gospel. For this grass, the permanent wilting, or better said, the dormancy point is about negative 500 kPa. So if we combine this whole graph that I've told you all about it, I've taken all these data, the water potential and the water content data, and I've combined them in the graph here. Now, by the way, we're not going to talk about this dark blue line. These are lab data, and that's something we did to make sure our lines matched, which they did. But our most important understanding here is creating our water envelope. So that's that 16% line right there. That's where we said we had a full bucket of water. Any more would just wash over the top of our bucket and run down through the soil. This lower line here, that's connected with this negative 500 kPa line. This is our dormancy line. That's when our bucket is empty. And so with this envelope, and not necessarily us wanting to irrigate completely to the bottom of that envelope, we can say with a 15 centimeter deep layer of soil, that's how deep the roots go. If we did a little calculation, we can see that the maximum that we'd ever want to irrigate the soil is about 12 millimeters of water. That would fill our bucket from empty to full. And so if you're ever irrigating more than that, you're washing water right over the top of that bucket. Can you see how powerful this is to combine these two things here? Now I have this beautiful envelope that's unique to this soil type. Remember, this is our loamy sand, and it has a particular behavior that we need to understand to irrigate it well. And it's not the same as a clay loam that we're going to talk about now. So this is a clay loam soil in potatoes. And the question is, can we go ahead and do the exact same thing for our clay loam? Again, what we're doing is combining water content and water potential together to give us a complete picture. Now, we still have water content on the left-hand y-axis and matrix potential on the right-hand y-axis. But here we're actually in Zenter Cloud, and I've been able to set up a nice zone here, this green zone, that tells me my optimal range. But maybe I want to know something about this, okay? I want to know what water content range I can work in and how much water I need to apply to this to go from empty to full. So I'm going to do this right here. So this is a green line that goes up to the upper range of water potential, negative 20 kPa. We're going to put a dot there. That's the maximum matrix potential we want in the soil. The water content in this red line, so the gray line is water potential, the red line is water content. So I match that water content on this line. Here's the water potential dropping down into the optimal range. Here's the water content, and that's about 23% volumetric water content. What's the lower limit? Well, the lower limit's right down here. So here's our gray line. It's exiting out of our optimal range. We'll put a dot right there. That's the lower limit we want for matrix potential or water potential. And we'll do the same thing we just did. Here's the water content at that lower limit. We'll draw that over here. So now we have as an upper limit about 23% water content and a lower limit about 19% water content. Now you might say, wait a second, wow, that's a pretty tight window. We only have 4% volumetric water content to play with. Well, that's actually true, but knowing that fact is a lot better than not knowing that fact. If you didn't know it, you might be looking up here at the water content and say, oh, that looks great. That's how much we fill with irrigation water. That's what we should do. Sorry, in this red line, up near 30%. Well, then you're over irrigating and you're washing water down through the soil. Okay, so let's do a little back of the envelope calculation. And we could do this a little more carefully, but even really quickly, we can tell how much water we should be applying to the soil. So here's our rough guess. This was 4% different. I just mentioned that. So we have a 4% volumetric water content range for our optimal range of water potential. Let's just assume that the rooting depth of our potatoes was about 50%. So if we have 4% water content with 50% or 50 centimeters of rooting depth, a little calculation tells us that we need 20 millimeters of water to refill from this lower limit back to this upper limit. This is a great thing to understand because suddenly we have the power to understand how much water we should apply. We can measure our precipitation and our irrigation, and everything starts to become clear. Okay, let's return back to the example that I started with of us young men in this cabin trying to figure out how to keep warm. This is the fundamental thing we learned, and I want you to take away today. We don't know if we'll be comfortable just by knowing how many logs we've added to the fire. You can't know without other information. In the same way, we won't know if the soil is optimal for plant growth just by knowing the water content. So here is a pop quiz. Here are data from another field. You can see the water content data here for the season. I'm not telling you anything about the soil type or anything about what we're measuring, anything like that. Don't make assumptions about it. I just went through an example that might look like this. It says 24% water content, but I'm not telling you where that is. We just have water content. So I want you to take a second to decide, do I have enough water, or do I need to water? Do I not need to water, or do I not have enough information? So I'm going to wait about 20 seconds and let you take this poll. So go ahead and take it. Okay, I have about 10 more seconds. Okay, 5, 4, 3, 2, 1. Okay, we're going to end. Great, thank you for doing that. So I'm going to tell you the results of this poll in just a moment, but I'm going to tell you the answer first. So, should I water? Well, if you answered not enough information, you were right. There wasn't enough information. Even though the water content in this soil said 24% water content, we don't know what that means. So it turns out that this soil was also a clay loam soil. And what was kind of weird about this example was that the water content flattened out here. So you may have said to yourself, I think we need to water because it doesn't look like the plants are taking up water here. But what we didn't know is what the weather was like. In fact, it may have been a cold, cloudy day that day, and it just didn't lose much water. And in fact, when we turn on what we really need to know if they're in their comfort range, the water potential, we quickly realize that we don't need to water because we go over here at this exact time, it's 24% water content, but the matrix potential all the way over here on the right-hand y-axis is at negative 34 kPa. And if you looked at our thermometer, that's just dead in the middle of our optimal range. And so we know we don't have to water. It's perfectly fine at this point. But even better, using Zenter Cloud, Zenter Cloud can help you keep your ranges right there. So you can see this beautiful green area where you're supposed to keep your plants, and you can see it's right there in the optimal area. So here's the results of the quiz. 75% of you guys got it right, with about 12% saying yes, 12% saying no, which was the wrong answer, and 75% saying not enough information. That's great. Good job, guys. Those of you who didn't get it right, I hope you see why we just didn't know enough to be able to answer that question and the importance of water potential in making that analysis. Now for a summary. Water potential should be understood like temperature. We shouldn't consider its complex definition. We should memorize the critical range for comfort and apply strategies to keep this within its boundaries. Water potential is difficult to measure accurately, but it's not impossible. Although some sensors have large variability and are not suited for field measurements of water potential, the individually calibrated Teros 21 sensors show excellent consistency. And I hope you've seen from all these data I've presented that Teros 21s can be effectively used in the field to make sure you're in the right comfort range, or even to know when you're in stress range. Finally, combining water potential and water content together is a powerful tool. I admit that it's straightforward to irrigate with only water potential, and I can see people doing it, and I think it's effective. But you miss how much water to add each time. Together, Water content and water potential give a complete moisture picture, and the comfort range generates the idea of the metaphorical logs to add to the fire that I talked about in my example. Now I'd like to go ahead and turn the time back over to Brad, and we're going to try to answer a few questions for you.
All right, thanks, Colin. So we do have a few minutes left for some questions from the audience. Thanks to everybody who's already sent in questions. We've got a bunch of questions that have come in already, and there's still time to submit your question. So we'll try to get to as many as we can in the next few minutes. If we do not get to your question, and again, please, any question that you have, type it into the questions pane. We will try to get to as many as we can. If we do not get to your question here during this live recording of the webinar, Colin or somebody else from our Meter Environment team will be able to get back to you and answer your question directly via the email you registered with. So yeah, don't be shy, ask those questions. We'll try to get to as many as we can. Let's see, Colin, we do have quite a few that are coming in asking about variation in soil type and how that affects working with water content in conjunction with water potential. So some people are asking about rocky soils or sandy soils or even other substrates, for instance, with green roofing or those kinds of things. What kind of advice or what can you give to those?
These are great questions, and maybe I'm going to defer to an opportunity to talk about this in a special virtual seminar that we could give to really address some of these issues, because I simply don't have time. The complexity of this may be too much to try to go into here. But think back to this example where I combined the water potential and water content together on one graph to make a moisture release curve. This is the best way that I know of to really fingerprint a soil, because the soil, every soil is unique. So if we put a water content sensor and a water potential sensor together and measure that, we can overcome a lot of the challenges that we have in these different substrates. But boy, if we talk about trying to go into a green roof material, usually an engineered material that's up on these roofs, that's a little bit complicated, and we need a specialized water potential sensor to go into that environment. And so that really is going to have us talking a little bit too long for this seminar, but to suffice it to say, in rocky soils and in sandy soils, we can do these things. In fact, a water potential sensor is great in something like a rocky soil because it's measuring an energy state and not an amount. Energy tends to go to equilibrium. So in a rocky soil, if we can bury that in a portion where we can make good contact between the sensor and the soil, it will tend to go to equilibrium, and then we'll be able to measure the energy state of that soil more effectively than a water content sensor that probably is going to get air gaps in rocky soil.
Okay. And as we're dealing with, we're under the presumption that many of the folks here are soil or plant scientists of some kind. How is it, and this isn't specific to soil and plant science, this is a kind of science broadly about speaking to the layperson. How can those folks who are consultants to growers, agronomists, or others, how can they easily, like you were talking about doing kind of the back of the envelope calculations, how can they easily communicate the impact of using water content and water potential together? How can they best communicate that to, for instance, a grower who might not have that same kind of scientific expertise?
This is a great question, and this is really what I was trying to do in this seminar today. And we'd love to reach out and start working together with each and every one of you to try to get people comfortable. I think there was a time, maybe Warren Johnson, who made that thermostat, maybe he was frustrated early on that people really didn't integrate this question of temperature and understand how this would be so powerful with the thermostat. But once they started to get used to these temperature numbers that were coming out, again, they didn't understand temperature is a fundamental thermodynamic process, but they did understand this comfort level. And if we can get people comfortable with using this standardized water potential thermometer and just those ranges, I think we're going to make progress, because no one is talking about temperature in their house anymore in terms of of the energetics of it or whether it works or doesn't work. They simply know. Here in the United States, you'd say, if 72 degrees, is that comfortable? Yeah, perfectly comfortable. Or 22 degrees Celsius, are you comfortable? Yeah, I'm comfortable. They don't know the fundamentals of it. They just understand the units.
Right. We do have several questions also asking about variability in water content and water potential throughout a field. How can they work through that or mitigate that issue?
So this is a great question. So I've been associated with several experiments who went out and measured water content in different treatments and then tried to compare them. It turns out it simply doesn't work. And we see that water potential is high, or water content, let me be clear, water content is highly variable in space. We've done studies where we've gone across a field and just measured the water content at 1 meter increments for 100 meters. And we've seen this just pop up and down. But as I mentioned, water potential is a process that tends toward equilibrium. And so all things being equal, as I showed you in those farm fields that are just overwintered and we're sitting there in the spring with nothing growing on them, their water potential was very, very close together, although their water content was highly varied. I could have showed you a slide to prove that. So if we're wanting to be able to compare sites and deal with variability, the ideal situation is have water potential sensors in there that tell you about a way to compare each of those sites. Now, if you want to know the amount of water and compare those things, that's fine. Bury them together and you can compare them through their moisture release curve, which in my opinion would be ideal.
Okay. I think we've got time for one more question here as well. Again, thank you for all your questions. We've got a flood of questions. I've been struggling keeping up with all of them scrolling through. So thank you again. And again, Colin or somebody else will be able to get back to you if we did not get to your question today. Again, a couple of people are asking, once they have figured out the relationship between water content and water potential within their specific field, their specific plant application, etc., do they need the water potential sensor anymore? Can they just rely strictly on water content?
So that's a great question. If you know your moisture release curve, do you need that water potential sensor out there? And the short answer is no, not really. You can use the water content for that. So in several experiments I've done, I've gone out and installed water content sensors, and then I've simply created a moisture release curve in the lab using meter groups high prop and WP4C, and then I've used that to turn water content into water potential. So that's perfectly reliable. Now for me, I like the water potential in the soil so much that I've just started using it on every single experiment. I don't want to just depend on this moisture release curve and just a great guess, but still a guess because the sensor's not there to know what the water potential is. So because water potential is so easily available now, and I can install a sensor that's accurate finally in the soil with the Terrace 21, I just do that. And then I'm sitting there watching Zenter Cloud in my office from Southern Idaho, during COVID where I can't go down there. I've got water potential streaming in. I know if those plants are in the comfort range there in Southern Idaho or my 2 projects in Utah or even in other countries, that's all coming in.
Awesome. Thank you, Colin. And thanks again for everybody who's attended. That's going to wrap it up for us today. We hope you enjoyed this discussion as much as we did. And again, thank you for all of your great questions. We will be able to get back to you and answer your questions. Also, please consider answering the short survey that will appear after the webinar is finished, just to tell us what types of webinars you'd like to see in the future. And for more information on what you've seen today, visit us at metergroup.com. And finally, look for the recording or a link to the recording of today's presentation in your email, and stay tuned for future Meter webinars. Stay safe and have a great day.